Swayam Prabha. Digital India. Educated India.
So, hello everyone, today I will discuss kinetics of protein adsorption. So, in the last class we discussed different methods to determine the adsorb amount as well as the property of the adsorb layer. So, for measuring the adsorb amount we discussed the labeling method, radioisotope labeling, fluorescent labeling. Then colorimetric method we discussed the Bradford method, BCA method and Lowry method. Also we discuss a few instrument based methods like quartz crystal microvalence, surface plasmon resonance, ellipsometry. Followed by the adsorb amount, we also discuss, we can see the rigidity or softness of the adsorb layer. If you can monitor the dissipation energy, and dissipation energy we discuss, we can easily monitor using the quartz crystal microvalence. So, from the value of dissipation energy or change in dissipation energy, one can comment on the viscoelastic property of the adsorb layer. And the next we discuss, once the protein adsorb on a surface, what is the change in the secondary structure of that adsorbed protein as compared to the native protein. So, for that we discussed using FTIR as well as the circular dichorism to measure the change in secondary structure. So, once we have experimentally measured the adsorb amount, so we have the kinetic data, means change in the adsorb mass with time. So, today we will discuss the kinetics of protein adsorption on a surface, what are the different processes are there during the adsorption process, like its attachment, then rearrangement. Also we will discuss how we study the kinetics of adsorption of single protein. Then at the last we will discuss briefly about the competitive protein adsorption, means the presence of more than one protein during the adsorption process. So, adsorption of protein, especially if you talk about the biomedical implant. So, we are having, this is the surface and this is a body fluid which is having water molecule, proteins and the cells. So, depending on their diffusivity they will reach to the surface. The first water molecule reaches, followed by protein, then cells. Now, once protein reaches to surface, there is a protein surface interactions, we are calling here as the adsorption of proteins, and depending on the various interactions between surface and protein, including van der Waals interaction, electrostatic interaction, dipolar interaction, hydrogen bonding, hydrophobic interaction as well as the entropic effects. So, it decides what will be the fate of adsorbed protein. It may be there in nuclei-like structure or it may denature. If it is unfolding or denature, its desired functions will be lost. So, depending on the surface property, we can tune the intermolecular or the protein surface interactions, and that can decide what will be the conformation of the adsorbed protein on the surface as well as what will be the adsorbed amount on the surface. So, these are the intermolecular interaction we have already discussed. Similarly, if you just see in this figure, depending on the surface, if there is no spatial arrangement here, so protein is trying to reorient itself. Protein is reorienting itself depending on the surface property. So, this is one example of the entropic effect. Also, during the adsorption, if there is some sort of unfolding, this will also lead to change in the entropy. So, as I told, once we know various experimental method to determine the adsorption amount with time, so we will have this sort of data. With increase in the time, there will be the increase in the adsorption mass. So, if you plot like this, time and mass, so it should typically go like this and reach to the plateau. Now, if you can analyze the kinetics of adsorption, you should be able to comment what is the rate constant. Or what are the different processes involved in the adsorption. So, we will come back to this problem. So, first let us see during the adsorption of protein what happens. So, typically if we just see here, this is protein in the bulk solution, it is coming on the surface. So, the first step is the adsorption and desorption. So, you can just see this is the adsorption and this is the desorption. So, the very first step is the adsorption and desorption, or you can say overall this is the attachment. And followed by attachment, there is a rearrangement or the reorientation. So, this next step is the conformational adaptation or the rearrangement. So, typically these are the two main processes involved during the protein adsorption: attachment and reorientation. So, when there is attachment, we call it a nucleic structure, and after the rearrangement we call it adapted conformation. So, a protein once it reaches to surface, it will have different conformation, and after relaxation or once it reaches to the equilibrium with the surface, it adapts to a different conformation. So, further we can see n number of steps during the protein adsorption process. So, here I have listed: first, protein itself reorients depending on the surface. So, it is reorienting itself, then it will reach to the interface, it is attaching and detaching to the interface. So, this is the attachment step, then followed by that there is a relaxation or the rearrangement, then it reaches here. Further there can be further rearrangement with time, although there is no conformational change, but there can be more relaxation with the time. So, there can be a further relaxation. Now, depending on the affinity of the protein on surface, there can be again a partly detachment from the interface, and this detached molecule may again go back to the very first step, that is the attachment or the adsorption at the interface. So, these are the, you can say, 6 main steps. first transport towards the surface or interface, then deposition and attachment at the interface, followed by the structural arrangement or you can say the relaxation. Then there can be more relaxation depending on the affinity or the surface protein interaction with time. And then this adapted molecules or the rearranged protein molecules can also detach from the interface, and after detaching it can again go back in the bulk or again it can come back to the main adsorption process. So, these are the multi-step processes involved during the adsorption of a protein. Now, we will quickly see the kinetics of adsorption. So, as I told, proteins are there in the bulk, from the bulk they are coming to the interface. So, this is the surface and this is the bulk. So, from there it will first come to the interface. Once it is coming to interface, then at the interface protein will have a different conformation, and after this rearrangement the protein molecule will adapt to another conformation. So, also we call this conformation like a side on, we call this as a side on, sometimes we call this as a end on. So, we call as a side on, it occupies less surface area, and side on it occupies some extra surface area depending on the its conformational changes. And this surface layer thickness is typically equivalent to the size of the protein. So, it vary in the few nanometer range. So, the protein molecules are there in the bulk, they come near to the interface, then they cross the interface. So, if they are crossing the interface, so there will be a mass transfer resistance. You can say the film mass transfer resistance, then there is to surface, then again there is a rearrangement or reorientation. So, the very first step is the protein molecules are coming to the surface from the interface. So, the transport towards the interface depends on the what is the bulk concentration, or you can say this delta C is the driving force, and this diffusion term is the resistance. So, the flux is proportional to the delta C into the diffusivity divided by T to the power half. The same equation can be rearranged in terms of K T R. The K T R is a mass transfer coefficient or mass transfer rate constant into delta C. So, it is like K into delta C. So, the first step. So, what is happening here? You have a different concentration in the bulk, and when it is coming to the surface it is having a different concentration CS, and that will depend on the value of diffusivity, or you can say the value of mass transfer coefficient. So, once protein reach to the surface, so the next step will be its attachment as well as its reorientation. So, here we are calling as a end on and the side on orientation. So, protein plus surface, it is forming a let us say intermediate P1S1. This is the attachment, here you can say adsorption, K2 is detachment or desorption rate constant. Then in the next step of the rearrangement, this adsorbed protein molecule will require some extra surface. The C is the fraction of the extra surface, because the surface area required for the end on and side on orientations are different. So, it will require some extra fraction of the surface C. Yes. Now, here again you can think of either reversible or irreversible. If it is reversible, we will have K3 and K4. If it is irreversible, we will have only K3, and it is now going to the P1S2 conformation or the side on orientation. So, it is coming to the end on orientation, then going to the side on orientation. So, these are the two main steps, attachment and reorientation. Now, depending on those equations, we can write the rate equation. So, rate equation will be P1 plus S K1 K2 P1S 1, it is taking some extra surface, it is going to the P1 . So, d P1S upon dt is equal to K1 into P into S minus K2 P1S 1, and P1S 1 will come from here, this is K3 and K4. So, K4 P1S 2 minus K3 P1S 1 into S. Now, similarly, we can write for the P1S2 d P1S2 upon dt, including this, it will be the K3 P1S1 into S minus K4 P1S2. So, these are the two rate equations. So, if you solve these rate equations, we can estimate what is the concentration of P1S1 or side on orientation, and what is the amount of P1S2 end on orientation. So, depending on how many unknown parameters are there, we can either solve it analytically or we can solve it numerically. So, that will depend on the how simple or how complex are the rate equations. So, I have listed let us say two very simple equations. First is A is in first step converting to R, and second step it is converting to S. Here we are assuming that in the first step rate of desorption is very slow, or we are just ignoring the rate of desorption, only the rate of attachment is taking. So, we are taking both as a irreversible and first order. So, the first step will be dCA upon dt, dCA upon dt, or you can say RA to minus, we are considering first order, can see K1 into CA. So, this will be like dCA upon CA minus K1 dt, integrate 0 to t, this we are going to integrate CA not to CA. So, we will end up with ln Ca upon Ca naught is equal to minus k1 into t. So, Ca upon Ca naught is equal to e to the power minus k1 into t. Now, let us go to the r. So, this will be like a dCr upon dt, or you can say rate of r. This will be k1 into Ca, k1 into Ca minus k2 into r. Now, you can just rearrange it. So, it will be like d Cr upon dt plus k2 r to k1, and Ca we can write from here. Ca is Ca naught e to the power minus k1 into t. So, if you want to solve this, so it is like a dy upon dx plus py is equal to q. So, if the solution for this is, so y into integration factor e to the power p dx equal to q into integration factor e to the power p dx plus constant. So, the value of integration factor is y into e to the power k2 t equal to the value of q is k1 Ca naught e to the power minus k1 t into integration factor e to the power k2 t dt plus constant. So, here we get the integration factor to e to the power p into dx. So, we can rearrange it. So, this will be like, if you solve this, so this will come like k1 divided by k2 minus k1 e to the power k2 minus k1 to t plus constant. Now, if t is equal to 0, this y will be, or you can say the y is the Cr will be 0. So, at t is equal to 0, Cr will be 0. So, if we put like this, so the value of constant will come. This term will be 1 and this will be the 0. So, it will be only minus k1 Ca naught upon k2 minus k1. So, if you put the value over here, so you will get the value of Cr is equal to k1 k2 minus k1 under bracket e to the power k2 minus k1 t minus 1. This whole will be divided by e to the power K2 into T. So, if you just divide this, so here the K2 will be cancelled out, here will be e to the power minus K2T. So, if you solve here, so we will get K1 upon K2 minus K1 e to the power minus K1T minus e to the power minus K2T. So, in this way you will be able to calculate the concentration of the R, Cr. Now, go to the third equation is the Rs. So, it is very simple, dCs upon dt is equal to K2 into Cr, or another way the concentration Cs will be Ca naught minus Ca minus Cr. So, Ca we have calculated here, Cr we have calculated here, Ca naught is known to us. So, we can also calculate easily with what is the concentration at the surface. So, here we have simplified that there are two steps, one is the attachment, second is the rearrangement, and both we followed or we considered the first order kinetics. Now, we can also consider one is the first order kinetics and second step is the zero order kinetics. So, if you consider the zero order kinetics, so the third Rs will be simply K2. First order kinetics, R is K1 into Ca, RR will be K1 into Ca minus K2, and the third step will be Rs is equal to only K2, and accordingly we can also solve it, and these are the solutions. So, what we have to do, we have to calculate the amount of intermediates, then finally we can see how the intermediates are changing with the time and how the final conformation is increasing with the time. Another aspect may be we can consider the first step as a zero order and second step as a first order. So, for the zero order Ra will be minus K1 and this Rs will be K2 into Cr. This is the first order and this is considering as first order, here we are considering as a zero order, and then accordingly we can solve them. And finally, in all the cases the Cs will be initial concentration Ca minus concentration of Ca naught minus concentration of the A, what is left, and concentration of intermediate Cr, how much amount it is there, because total concentration will be Ca naught, that will be constant. So, here is one example where the two proteins, one is fibrinogen, other is the bovine serum albumin, their adsorption was studied on the surfaces with different functional group, or you can say different wettability. So, what you can see over here, it is plotted as the ratio of PS2 upon PS1. It means PS2 means final conformation, PS1 is the intermediate conformation, or you can say the side on orientation divided by the end on orientation. So, what we are seeing over here is initially there is a increase in this ratio, then there is a further decrease in this ratio. So, what does it mean is initially with time there is a different amounts of PS1 and the PS2, and slowly PS1 is converting to the PS2. So, accordingly their ratio is changing, but at the end both PS1 and PS2 are present on the surface. Now, one more thing, all the surfaces are not following the similar trend. It means that depending on the surface chemistry, there the rate of conformation, or you can say the rate of attachment as well as the rate of reorientation varies. So, here especially if you just see in case of octyl, so here the PS2 is the maximum, then again it is decreasing. So, this is how the intermediates kinetics are changing, while in other cases for fibrinogen this ratio is increasing. While in case of albumin, all the surfaces are following the similar trend. This ratio is maximum at maybe around 100 or 150 second, followed by there is a decrease in that ratio. But again, if you just see the rate of increase, rate of formation of PS1 and PS2, it varies. So, the rate of adsorption, or you can say the rate of attachment or the rate of rearrangement, it depends both on the protein as well as on the surface. So, we are having the same surface, but two different proteins, and we can see the rates are different. So, the rate, it depends both on the protein as well as on the surface. It is a very good example. So, we are having different surfaces and two different proteins. So, on the same surface two different proteins are following the different adsorption behavior, or you can say the different rate of adsorption. So, that finally, the adsorbed amount as well as the adsorption process will be different. Now, we can work out on this example. So, let us say this is time and this is the adsorbed mass. Let us consider is very much first order kinetics. So, these are the black dots are the your experimental data points. So, let us say we can say m t mass at time t is equal to m max 1 minus e to the power minus k 1 t. We are considering overall adsorption process as a first order kinetics, that is mentioned here. So, we can fit this expression to this reported data, and we can get the value of k 1, and that value is k is coming out to be 0.29 hour inverse. Or the other option is the graphical method, means we can simply plot this is t, we can plot minus ln, you can say Ca m t minus Ca max m max. So, if you plot this, then again whatever the slope will come, that slope will be slope is equal to k. So, either you can fit this expression to the reported data, experimental data, or you can plot the ln Ca upon Ca max or Ca naught versus t, and the slope will be the value of rate constant. So, here the rate constant value for this adsorption data is coming out to be 0.29 hour inverse, because here we are considering the whole adsorption as a first order kinetics. So, now we can summarize, like during the rearrangement and adsorption, what is the role of different intermolecular interactions. So, when the protein comes into the contact, the first interaction is the van der Waals interactions, because it is a long range interaction. So, here the plus sign indicates it promotes the adsorption process, and negative sign indicates it opposes the resists the adsorption process. So, van der Waals interaction will be there and long range. So, it will favor the adsorption process. Now, once it comes near to the surface, so depending on the charge groups of the surface and the protein, the second will be the electrostatic interactions. If they are opposite charge, it will favor the adsorption. If they are negative charge, they will repel each other. Now, first step is the van der Waals, then electrostatic interactions. Now, After this, depending on the surface hydrophobicity, the water molecules will come to the surface, or you can say there will be the dehydration of the solvent surface and the protein, and that will depend on what is the hydrophilicity or hydrophobicity. So, if it is if it is a hydrophobic surface, means it is going to have the hydrophobic interaction. If and for the hydrophobic interaction, again it will promote the adsorption of the protein, while hydrophilic surface, the water molecule will come in between the protein and the surface. So, this inhibits or resists the protein adsorption. Now, followed by this, there will be the structural rearrangement of protein, which may also affect the intramolecular hydrogen bonding. Means now we are talking about the making and breaking of different hydrogen bonds. So, if there is a formation of hydrogen bonds with surface, then there will be increase in the, it will promote the adsorption. If there is no increase in the hydrogen bond, or you can say the intramolecular hydrogen bonds are intact, then this will not promote the adsorption process. Similarly, there may be the formation of hydrogen bond between the surface and the protein. Now, after this there will be the structural rearrangement of the protein, which will affect the conformational entropy, because if there is unfolding or rearrangement, there is going to increase in the entropy, and if there is a conformational increase, or you can say if there is a unfolding, which is again going to promote the adsorption process. If there is no conformational changes, then adsorb amount will be lesser as compared to the reoriented or the conformational adaptation cases. So, what we are seeing is there are different intermolecular interactions are taking place, depend on the chemistry of the protein as well as the chemistry of the surface. The first step will be the van der Waals or dispersion interaction, that is irrespective of the surface chemistry. Now, if the surface is charged or there are some charge residue on the protein, so if they are oppositely charged, there will be the positive electrostatic interaction, which will promote the adsorption. Now, next step will be the water layer, it will depend on the whether this is hydrophobic surface or the hydrophilic surface. Then there is a structure rearrangement depending on the making and breaking of the hydrogen bonds, and finally, there will be the entropic effects or the conformational entropy, and these intermolecular interaction and rearrangement will finally decide what is the adsorb amount and what is the conformation of the adsorb amount. So, you can say the protein adsorption is a multi-step process, and it is having a complex intermolecular interactions depending on the surface chemistry, hydrophobicity, charge of the protein as well as the surface chemistry, hydrophobicity and charge of the surface. Apart from that, also what is the ionic strength of the solvent or the environment, that will also affect these intermolecular interactions. Now, let consider the competitive adsorption. So, this is the first one where we are considering the single protein adsorption. We are having two steps, attachment and reorientation. attachment and rearrangement. So, protein molecule is coming in the side and end-on orientation, then it is going to the side on orientation. Now, if you are having two different proteins, let us say one is the BSA and other is the either fibrinogen or the IgG. So, BSA is the smaller protein, its molecular weight is for BSA it is equals to 66 kilodalton, and for IgG it is let us say 150 kilodalton. So, what happens in case of competitive adsorption, the smaller protein molecule will have the higher diffusivity. The first step, the smaller molecule reaching on the surface, it will have both end-on and side-on orientations. Then once the larger protein molecule is reaching on the surface, it will try to replace the smaller protein depending on the affinity of the surface and the smaller protein. So, here you can see all the end-on oriented BSA molecules are replaced by the bigger protein molecule either FB or IgG, and further again there will be rearrangement of that larger protein molecule as well. So, first there is a adsorption or attachment of a smaller protein, its rearrangement, then there is a replacement, or you can say this is the displacement of smaller protein by the larger protein. Again the larger protein will go for the its rearrangement or the conformational adaptation. So, the one extra step during the competitive adsorption process is that displacement. And that displacement depends on the affinity of that smaller protein with the surface, as well as the what is the which one is the smaller protein or the larger protein. So, typically the Roman effect says the larger protein displaces the smaller protein or initially adsorbed protein with time. So, it says displacement of initially adsorbed means smaller protein by a second protein or the larger protein. So, the smaller protein is replaced by the larger protein. So, again you just see although the adsorption process remains same, but one extra step of the protein interactions or the displacement of that protein molecules is coming in the picture. Now, if you just see here, once the proteins are there in the end-on orientation like this or the side-on orientation like this. So, the protein surface interaction in the end-on orientation will be lesser as compared to the side-on orientation. So, once the larger protein molecules are coming, it will be easy for them to replace the end-on oriented protein. So, we have studied this adsorption behavior of BSA and let us say fibrinogen on different surfaces, and here if you just see in the competitive adsorption all the end-on orientations are 0, means all the end-on orientations have been displaced by the larger protein fibrinogen. Now, again if we just see the octyl surface, it is octyl is a hydrophobic surface. So, in this case the affinity of the protein and surface of even for the smaller protein is higher. That is why all the end-on adsorbed proteins have not been replaced by the larger protein, but at the same time now you just see in all the cases the smaller protein having some fraction of the side-on oriented protein. It means it is easy to displace the end-on adsorbed protein. So, the smaller protein which are adsorbed in the end-on orientations are typically displaced by the larger protein, while the side-on oriented proteins are not easy to be displaced. Now, let us see for the other protein. Now, this other protein, larger protein will have both the fractions end-on as well as the side-on. So, it is following a typical adsorption process depending on the availability of surface, because first smaller protein will reach to the surface, it will occupy some surface space, and depending on the available surface space a larger protein will come, it will try to displace the smaller protein, and typically what we observe in this case, let us say these are the end-on. So, in this step end-on adsorbed smaller proteins has been displaced by the larger protein, and then again the larger protein is going to its rearrangement. So, it is having the presence in the both end-on as well as the side-on orientations. Again this displacement depends on the affinity of surface. Typically, if you see in this octyl case, the binding of the protein surface is strong enough to be displaced by the larger protein. So, what we have observed is during the competitive adsorption there is one extra space displacement is coming, and that depends on the size of the smaller and the larger protein as well as the affinity of the surface and smaller protein. So, here I will conclude. So, we discussed today what are the multi-step process during the adsorption of protein. So, very first is the attachment, it will have the adsorption and desorption followed by its conformational adaptation or the rearrangement, and the rearranged protein can also get dissolved and it will again come to the very first step of the adsorption or attachment. So, in this way there are the multi steps involved during the adsorption of the protein, and during the kinetics of adsorption the very first step is it is coming from bulk to the interface. So, there we are having the diffusion resistance, or you can say the film mass transfer resistance, then it is coming to the surface in one orientation we called here as a side on orientation, then it is getting arranged to the end on orientation. So, if you want to solve or determine the kinetic parameter, so we have to solve the rate equations, and the rate equations if they are simple we can solve analytically, otherwise we have to go for the numerical solutions, and we discussed few simple examples of the A to R to S, both first order kinetics, or one is the first order, second is the zero order kinetics, or one is the zero order, second is the first order kinetics. So, depending on that order of the reactions or order of the one step and second step, we can calculate the amount of the intermediates as well as the amount of the final concentrations. So, in that way if you know the solution of that adsorption equations, we can calculate the intermediate formation as well as the rate of attachment, rate of reorientation or rate of desorption. Then next we discuss the formation of intermediates or the rate of adsorption depends on the protein as well as on the surface. So, we discussed one example where on different surfaces we use two different proteins, albumin and the fibrinogen, and in both the cases the formation of intermediates as well as the rate of attachment and reorientation were different. So, we observe the different concentration profile for the intermediates on different surfaces. Then we just discussed what are different intermolecular interactions which participate during the rearrangement or adsorption of the protein. Then finally, we briefly discussed the competitive adsorption. So, during the competitive adsorption, one more extra step, displacement is involved apart from the attachment and the reorientation step, and that displacement depends on the size of the two proteins. We discuss only the binary, but there can be the mixture of proteins. It may be ternary or the more mixture, especially if we talk about the body fluid, it is a mixture of many proteins. Then the displacement depends on the what is the affinity of the smaller protein with the surface. If it is having higher affinity, it may not be possible to displace by the larger protein. So, the Browman effect may not work depending on the affinity of the protein and surface. Thank you.